integration, so far we've learned to apply formulas to find the integral or antiderivative of a function. Unfortunately, there are many integrals that we just don't have any formula for. As simple as, say, square root of 1 plus 4x dx. So there's no direct formula for this. Or let's look at the sine 2x minus 1. Want to integrate, want to find the antiderivative, there's no formula. So what we do is to try to apply what's called integration by substitution technique to do it. The idea is to think of 1 plus 4x as a new variable. So if 1 plus 4x as a new variable, we would have a square root of this new variable, where square root is just power, half power. So basically this would be turned to power of a new variable, which we have this integration of a power formula available. So this is a integral of power equals 1 over n plus 1 u n plus 1 plus c. Right? So it's a change of variable or substitution by new variable. Same idea here. With the sine 2x minus 1, there's no direct formula. But if we think of a 2x minus 1 as a new variable, say u, we usually use u. And that's why this method is sometimes called u substitution. But anyway, if we think of a 2x minus 1 as u, then this would become sine u. Just a very simple, basic function that we have actually integration formula for. All right, so let's actually work it out each case just to get the idea of what's going on. So like we talked about, we're going to think of this as u. So in writing, so we're going to introduce substitution because u equal to 1 plus 4x. All right. With this substitution, now the integral, so let me copy down the integral here. The integral becomes, well, just square u, or half power of u. Half power of u. Notice though, this is the integrand. The integrand becomes power of u, as we hoped for. Then there's dx. We're not going to copy down the dx because it's wrong to have two different variables, the old and the new, in the same integration expression. So cannot do that. We cannot just turn dx to du. It's not usually the case. What we do is to figure out how to replace dx, figure out what we have to substitute in for dx. How do we do that? Well, we worked on the side based on the substitution. So if we differentiate on both sides, it would be du equal to negative 4 dx. So find the differential on both sides. Differential of a function is function prime times dx. So you can see on the right side of the substitution, if we differentiate, that's f prime, we get 4. And multiply by dx, we always multiply by dx. From here, we solve for dx. So divide both sides by negative 4. And then we see precisely what we can plug in for dx. It's pretty simple. So let's plug in. See? So you see two things. One, you cannot just still have dx there in your new integral involving u. Two, you cannot simply replace dx by du. exactly what you have to plug in, you need to work on the side in writing to figure out every substitution problem. Now we continue. So negative 1/4 move out, that's constant. Then just apply power formula. So 1/2 is power according to our integration of power formula here. The answer is 1/n, or half. Power is half, sorry. 1/power plus 1 u raised to power plus 1 plus c. And then simplify. 1/2 plus 1 is 3/2. 3/2, so flip it to 2/3, and the u replace back by, it's minus 1 it's 1 plus. Somehow I got 1 minus somewhere. Okay, let me fix it. So what I got is minus, so let's stay with minus. This is minus. So less correction I have to make. All right, it says minus because in my substitution I got 1 minus the differentiation relationship. I got 1 minus, so let's just stick to 1 minus. Sorry about that, but anyway. So the key is in the back here. Once you're done integration, you're going to plug it back. 1 minus 4x for u, and then the power, of course, is 3/2 plus c. So finally, you got 1/6, 1 minus 4x, 3/2 plus. All right, let's see next example. So again, like we said, we want to consider, in this case, 2x minus 1 as a new variable u. So write it down. U equal to 2x minus 1. At the same time, just find the differential right here, because we're going to have this anyway. We're going to need this and solve for dx. Divided by 1/2. Now the integration. So integral of sine 2x minus 1, we wanted to do, becomes sine u, that's the integrand, that's turned to a function of u, and the dx, according to what we already find here, is 1/2. Oh, let's have black color. 1/2 du, and you pour out the 1/2 du. You apply formula, which is cosine u plus c, and finally replace u back by 2x minus 1. All right, so this is how substitution technique works. Try to come up with a substitution that's going to turn the given integral to an integral for which you can apply existing formula. Let's see more examples. So here I have an integral of 1/cubic root of 1 plus 2x. Obviously, we don't have any formula for this. But if we think about it, first of all, the cubic root is power. It's in the denominator, so it's a negative power. It's still power. That's no problem. The problem is 1 plus 2x. We don't have a formula for power of 1 plus 2x. So, but if you think about it, if we think of this as u, then the denominator becomes 1/3 power of u, or move it up, it will become negative 1/3 power of u. Then that shows we're going to eventually apply this formula to do it. So let's put it in writing. So first of all, write down your substitution u equal to 1 plus 2x. And of course, just do that right away, because we need this anyway. Your dx will equal to 1/2 du again this time. Now the substitute the integration, because so the integral will equal to then 1 over cubic root of u. Well, dx becomes 1/2 du. If we do the transformation, first of all, pour out 1/2. Let's turn this to a power, so this becomes u to negative 1/3 power. Okay, cubic root is 1/3, but if you move it up, it becomes negative 1/3. So we apply, like I said, integral power formula up here. It's be 1 over negative 1/3 plus 1. U raised to negative 1/3 plus 1 is 2/3. So 2/3 plus c. And finally, can simplify it as negative 1/3 plus 1 is 2/3. And you flip it, 3 over 2, so it'll be 3 over 4. Be 3 over 4, just to simplify the numbers in the front, and plug in 1 plus 2x for u. Alright, this be the final answer. Next, let's see integral of e to 1 minus x. And then obviously we don't have formula for that. So we, however, realize if we regard 1 minus x as u, maybe simply e to u, then we have a formula for that. So our substitution will be u equal to 1 minus x, and du in this case will be negative 1 times dx, or dx equal to negative du, that we can use. Without this, our transformation is the integrand becomes e to u, the du becomes negative du. So pour out the negative e to u du and apply the formula. Very simple. E to u is e to u. Integral of e to u is e to u. So we just have e to u plus c, and of course bring back x. So 1 minus x for u. Alright, so these are all very straightforward substitution. With the substitution, we can turn clearly the given integral to an integral for which we can apply some formula right away. Now let's see some more complicated integrals. So these integrals all have one thing in common. So it's not simply one expression. Instead, the function or integrand contains usually like 2 parts. All right, like the integral here, there's x squared, that's one part. There's a square root, radical, that's another part, right? So we already kind of sensed the substitution, will somehow simplify the expression, so a formula, can be applied. But then now there are 2 parts we have to, deal with. How do we do it? Well, turns out it's pretty simple. And what we do is to first of all kind of clearly understand the two parts structure, and most of the time we focus on the main part, which is a more complicated part. So focus on the more complicated part. In this case, with the x squared, with the square root of whatever, clearly this is more complicated. So when we try to think of a substitution, we focus on the more complicated part. Simplify that. Most of the time, things would just work out naturally. All right, so let's see. With this problem, the more complicated part is this. So we're going to focus on that. So with this, what could simplify this square root? Well, that's clear. We just say, hey, let's treat it as u. Okay, let's treat it as u. So let's start to kind of transform the integral. So square root of 1 minus 3 times x to the third power then becomes square root u. All right. Then there's a dx left. There's also x squared left, right? And it turned out most of the time x squared and dx will be taken care of automatically as we try to find how du and dx are related. After all, we always have to get rid of dx, right? This time, there's also x squared that we need to get rid of at the same time. So you can see as we try to find the differential, du equal to this time negative 9x squared dx, we actually happen to have them together. X squared dx. This is just perfect. So we basically just solve for this. Instead of like in simpler situations, we solve dx. In those integrals before, there's nothing else we need to take care of. Well, here in this integral, there's x squared we need to take care of. But this equation shows x squared and the dx together, x squared and dx together can be taken care of at the same time. Why not? Just perfect. So we're going to solve for x squared and dx by dividing both sides by negative 9. With this, then we see just nicely x squared and the dx can be replaced by negative 1 over 9 du. Well, square root of u here is raised as half power. From here, which is simply apply power formula. Of course, copied on the negative 1/9. Half power formula is 1 over half plus 1. U raised to half plus 1 is 3 over 2, 3 halves, plus c. See, okay, just like before. And then you continue to simplify. 1 half plus 1 is 3 halves. Flip is 2 over 3, so it will be negative 2 over 27. The u replace by 1 minus 3x to the third power, 3 over 2 plus c. Alright, this is the final answer. Okay, so the two parts, just the integrand, that's more complicated. Let's see the next integral. So again, there are two parts. You can see there's x, there's cosine 2x squared plus 1. Clearly, cosine is more complicated. But then, again, if we try to regard 2x squared plus 1 as u, this more complicated part will become just simply cosine u, and we have a formula for cosine u. So let's try this substitution. So u equal to 2x squared plus 1, and du equal to 4x dx. Now, let's not solve for dx. Let's see what we should solve for. Well, if you start to transform the integral, you see the cosine part becomes cosine u, and you're left with dx and x. And that's perfect, because here we see x and dx together is the same as 1/4 u if we divide both sides by 4, which means x here and the dx here can be replaced at the same time by just simply 1/4 u. So pour out the 1/4 like always, and use the integral formula. Integral of cosine is just a sine. All right, and then finally, put the 2x squared plus 1 back for u. Constant. To find the answer. Right? Let's see more examples. So here again, two parts. So the two parts could be two factors in a product, or numerator and denominator in a fraction. So here's we see in a fraction there's x squared, there's square root, and this is more complicated. So we have to focus on that. Now how we do it is naturally we want to substitute in u for 4 times x to the third power minus 1, and do the differential, become 12x squared dx. All right, so now we can start to make a change in the integral. So the bottom, more complicated part, becomes the square root of u. X squared times dx left, x squared dx left together, we can see from here, and that's 1/12. So if we divide, therefore in the integral, x squared dx can be replaced together by that, and this is u to negative half power. Okay, this part. So we do integration, copy the 1/12, apply formula, power formula, 1/power plus 1 u raised to power plus 1 plus c. And that is, let's see, negative 1/2 plus 1 is 1/2. Flip it is 2, so it's 6. It's 1/6. And then the u replaced back by 4x to the third power minus 1. And the power, negative 1/2 plus 1 is positive 1/2 plus c. And then this is our final answer. Let's see one more. This time we have a cosine times sine of sine. Looks complicated. Well, particularly this part is complicated. It's more complicated than the cosine. Okay, so we'll focus on this. Of course, the idea is to think of this as a new variable. No big deal. So think of this as a new variable. Then du equal to just cosine x dx. With this, we can see the integral becomes, well, the main part. First of all, the main part will become, the more complicated part will become sine, simply sine u. See nicely, the cosine x and the dx together can be just replaced by du. So the original integral becomes just really simple integral. The answer is negative cosine du plus c. Of course, finished up, we're going to plug in sine x back for u plus c, and that's our final answer. So this is how substitution technique works. Now, in this simpler case, it's very clear, with the substitution, you end up with a simple power or simple sign, simple explanation. With more complicated structure, with the two parts, right? There's one way you can even check whether substitution would work. Sometimes substitution doesn't work, okay? It's good to know in advance. People even try to do anything, find the differential, start the transformation, so on, right? How do we do it? So let's take this problem as an example. So like we analyzed, this is more complicated. We would simplify this part. We would treat 1 minus 3x third power as u. So that's our substitution, and turn out it works, right? But how do we check before even we do any detailed work whether this substitution makes sense, would work at all? Say this substitution u equal to 1 minus 3x third power, right? You can quickly differentiate. You can quickly differentiate this part. What do you get? You have 0 minus 9x squared. So basically it's a negative 9 times x squared. Forget about the negative 9, the constant. So you would have a square. When you differentiate, you get the square. Now, I call this a supporting factor. So if you're going to try u equal to 1 minus 3x third power as your substitution, you can have this x squared ready, as you saw here, right? You would have this x squared right there. But this x squared better be what you actually have, cannot be any different. If you didn't have x squared right here, if you had x to the third power or x to the fourth power or any other power other than square, this whole thing would not work. Would not work, nicely, easily. In most cases, it would simply just not work. So here is the concept of a supporting factor. For this integral, for this substitution to work, we have to have x squared as a supporting factor, which we did. That's why it worked. So same here. We try the substitution u equal to 2 minus 2 times x squared plus 1, right? If we differentiate, we see 4 times x. So again, ignore the 4, just the x, which we have. So this x is perfectly the supporting factor. All right. So you can see, whenever you think of some substitution, whether there's any supporting factor, make it work. This is true for each every problem we did. Like here. So our substitution was 4 times x to the third power minus 1. We differentiate, it'd be 12x squared, which we have. So we have the supporting factor. And the last example we worked out, our substitution was u equal to sine. So if we differentiate the sine, we see cosine, which we have. So we have to have the perfect factor, I call supporting factor, in place for substitution to work. All right. So this is generally, how it would work out. You have to have a supporting factor. Now I want to show you some unique situation where apparently you don't have a supporting factor. So let's see. We have x to the third power square root of x squared plus 1. Okay, if you try the substitution method, focus on more complicated part, come up with your substitution. Let's put it in writing, so it's easier to explain. So this would be what we'll try, right? Our substitution. The problem is, if you use this supporting factor method to check it out, you would differentiate. You would have 2 times x. You would need the first part of x as supporting factor. We don't have that. We instead have a third power. So normally we say this way would not work, because x of the third power is not the perfect factor. It's not a supporting factor we expect. Then in this case, turns out it would still work because of the third power that is in some way nicely related to square. Let's see. So we'll go ahead. There's no other way anyway. There's no formula or whatever directly, right? Let's just go ahead. So let's differentiate. Then again, you can see when you differentiate, you expect first power to be the perfect factor, supporting factor, right? Unfortunately, we don't have it. Then we'll see how we're going to deal with the extra third power. All right, so this time you can see it would still work out, because the third power is just not any random thing. It is in some way related to the substitution and the actual perfect power or supporting factor. Let's see how. Now let's first rewrite. So according to our differentiation relationship, we actually would only need the first part of x. So let's in the integral, let's just take out a copy of x. You can see why this case it will still work. Just take a copy of x, put it in the back here. See, we start with the third power, so take a copy, becomes the second power with the copy here, right? So because of the differentiation relationship, we know these two together can be replaced by, like always, 1/2 du, right? Divided by 2. So we know this part can be taken care of. The more complicated part, of course, will become just square u nicely. The leftover is the key. Leftover, usually we don't have this. If we had the perfect supporting factor, first power of x, this would not be there. Well, here reality is we have it. What do we do? We can replace it, because this guy appears in the substitution, which means we can solve for x squared from there to see that this leftover can be replaced by u minus 1, right? So the leftover, in this case, you can see square, we can do it, the fourth power, we can do it. So in the original integral, third power, it will work out. You can see eventually when we finish the problem, fifth power would work too. If it was fifth power, we would have second power as leftover here. We would have a fourth power left over, but the fourth power is basically square of this guy anyway. Okay, so as long as, as long as your leftover is related to the substitution in some simple fashion. If it's more complicated, well, you probably have to do something else. But if it's related to your substitution pretty simply, can still be done. The substitution can still work out. So let's see. So in the end, we see that, let's take care of the main thing, the radical, the square root. So square root becomes square u, right? That's the main thing. The x dx together, we already saw that it becomes half du. The extra, x squared, the leftover, we usually don't have in the case of the presence of perfect supporting factor, right? Fortunately, in this case, can be replaced by rather simply u minus 1. So we do have a more complicated new integral. Can be done though, that's the key. All right, so pour out 1/2, and the u minus 1 times the square u. Well, remember, you cannot just integrate directly, you have to multiply through. U to have power u squared root is u to have power. So multiply through. Algebraically, you have u to 3/2 power minus u to half power. So no big deal. We just have 2 powers. That's 1/3/2 plus 1 u raised to 5/2 minus 1/2 plus 1 3/2 plus c 1/2 times 5/2 2/5 2/5, and the u replaced back by x squared plus 1 5/2 half plus 1 is 3/2 2/3 x squared plus 1 3/2 power plus c. So this is how it's done. This is just one of those like unique situations when you try to analyze the situation, especially you want to use the supporting factor, which I always do, right? In many cases, majority of the cases, supporting factor check can tell us whether the intended substitution would work or not. So anyway, so in those special cases, you try, oh no, we don't have the supporting factor. It's a third power instead of a first power. But it turned out because the leftover is related to the substitution itself in some simple fashion, this will still work out. You would just go ahead, focus on the main part, the more complicated part, square root, and take care of the dx along with the x, because that's actually the supporting factor. So basically you split like how I showed you, split the third part into first part you need for the substitution, and the leftover, whatever that is, and figure out how to deal with it, solve for x squared and get it here. So x squared becomes a u minus 1. The more complicated part becomes the square root. These two together becomes, number times du, work out. Turned out pretty easily too. All right, let's stop here.